very much for inviting. Okay.
Oh, yes, that's right. That won't work because you have to press got it on this one.
No, it's fine.
Everybody's seeing this meeting is being recorded. Are you able to navigate to that?
Press good on that one.
Maybe you have to use the arrow. Super.
Yeah, well, okay. Thank you very much for inviting me. This is the second physical conference I've done since COVID, the last one being just Monday, a couple of days before, where I was at Kubernetes. And it's fabulous being back physically presenting to people. It's much nicer than virtually presenting. And I've done quite a few virtual presentations over the last year and a half. It's nice, you've got a larger reach, but the physical presence is just. So I'm just going to go straight into my talk. I have a slide about me at the end, but I'm not very interested in the talk is. And there's about 20 slides. So if you want to see how far you are from the sure, does it show? It doesn't show a slide number at the bottom. I think it's out of reach there. I'm going to go straight into what is reliability engineering. And it sounds like it's making things more reliable, avoiding failure. But it isn't, because that's incredibly expensive to do. So it's actually about failure management, because failure is totally inevitable. You can't avoid it. There's always going to be something out of your control that's going to cause a failure in the system. So it's really about managing the failure and deciding how much failure is acceptable to you. And there's a talk, there's an article that I wrote there. It's all of my reliability articles are on Medium, so if you just search Jack Shirazi on Medium, you'll see them all. And this particular one is about Amazon's Route 53, which is the only major product which has a 100% reliability guarantee. They actually guarantee 100% uptime. Now, of course, there's small print there, so it's not actually 100% for every single person or every customer. It's 100% for their service, but there can be outages for customers, although they're only expecting a few seconds of outages. So they presented a talk about how they achieved that. And there's a huge amount of effort involved. So your average project has a certain amount of development time and typically 20 to 30% extra time for testing. In the case of, so this is Amazon's DNS product. In the case of their product, 90% of the time of the overall project is testing. So, and that 10% is still the same 10% that you have to do in your development time. So that's actually an order of magnitude larger in overall time taken. And that's just one of the costs. There's a whole host of costs. They have to reject most feature requests. Or if they really want it, but it's not going to keep the product stable enough, they have to find a way of putting it in, but not into the main path. So there's a lot of re-architecting of avoiding anything that's in the main the main feature path of providing a DNS service. They came up with an entirely new algorithm called shuffle sharding. So sharding is sharding. You know what sharding is? Just putting things in one sort of little area, and it's common for data storage. You have a shard and you have a replica of the data. So if the primary shard goes down, the secondary one takes over. So that's great. That gives you a level of reliability. Data storage is got all the time for reliability. So what Amazon thought about was, hang on, although it's unlikely that both those two particular nodes holding those particular shard data would go down, it is possible. How can we minimize the effect of that? So they said, okay, we'll have a group of customers in this shard, and instead of having a replica of that group of customers in another shard, we'll take that replica and we'll slice it up and spread it amongst all the other different shards. So that means that if this shard goes down and the nominated replica shard goes down, actually it only affects a very small minority of customers, not a whole cluster, but only a tiny number. It's called shuffle sharding. They came up with that specifically for this. And if you look at the article, there's a list of the other things that they do. And my focus in the article is just how expensive it is to make things 100% reliable. And every step is more and more expensive to get there. So basically, if you want, say, availability at 99%, it's 10 times more expensive to get up to 99.9%, and then 10 times more expensive to get up to 99.99%. And so every additional 9 is 10 times more expensive. And in fact, when I did the analysis, 10 times more expensive is conservative. It's likely to be more than that, which is one of the reasons why 100% reliability is not what you want, because all of your business leadership are going to come back and say, why is this so expensive for that tiny extra level of reliability? We don't mind being down for an hour or two to save millions. Oops. Okay, so I've discussed reliability is actually managing failure, deciding just how much failure you're willing to do. To see if there are failures, you tend to have incidents. And the most recent major outage was the Facebook one, I think it's about a month ago now. And that was a 6-hour outage of Facebook. In fact, I wrote another article here, the one about the bug already present, those 3 fastly, Google and Amazon. Facebook would sort of creep into this, but it's not actually as bad as these, because all 3 of these are major internet infrastructure providers. So when they go down, a lot of other companies go down. And whereas when Facebook goes down, it doesn't actually have that big an effect, even though it does make the headlines and it seems incredibly bad.
It does impact their share price.
Yeah, and it does affect their share price. And the conservative estimate for what it costs Facebook for that recent incident is $100 million for their 6-hour outages. And that was a conservative estimate. So if you're going to spend $100 million, you might as well make some benefit from it, right? So that's why incidents are unplanned investments. That's $100 million worth of investment there. You might as well want to learn from it. So whenever you have an incident, you should have not a post-mortem, but an analysis of what you can learn from it and how you can benefit, how you can improve your systems. And almost all incidents are categorized in various ways, typically by the team that's doing this. It's the landing page or the booking or the payments, something like that. And that's fairly useless as a categorization for learning. That's more about allocating blame, which we really don't want to do, or it might be about helping that team focus. But what I'm interested in and what you should be focusing on is categorizing by how you can learn from the incident. So this category list here, from monitoring down to latent bug, these are analysis which looked at a large number of incidents and found these categories applied in terms of the volume of incidents, not in terms of the cost of incidents, because the one at the bottom there, which is the smallest of this particular volume, the latent bug, was the most expensive, because that's, as you can see from the article, that's all of the outages were caused by latent bug, including the Facebook one. So the Facebook outage was down to a human error, but if you don't expect human error in any of your processes, then you're in the wrong industry, right? You have to assume that there's going to be human error. So you have to take account of that and assume there will be. And so in Facebook's case, there was actually a check for exactly what the person who was, the operation he was doing was basically updating how Facebook is found online. And there was a check for that, but there was a bug in the check, and that's the latent bug that Facebook had. So the check should have prevented the error, and it didn't because there was a bug in the check that caused the check to roll out. Basically took Facebook out of the internet, so you couldn't find it, which is what the cause was. And the reason in their case that it lasted so long is that because they had built their infrastructure based on at least some of Facebook's servers being available. So, so they couldn't fix the problem because none of their servers were available. And they had to actually break into one of their data centers and physically try to fix it. And the other ones here, Fastly didn't give a lot of details, but what they simply said there was a latent bug. It was in their system and it was triggered by a customer a long time after it was there. The Google one is that they rolled out a change to their major internal resource accounting system, and it had a bug in it, but the bug wasn't triggered until about 6 weeks to 2 months later. And that was from an upgrade of another system, which then triggered that bug. And in the case of Amazon, they were doing something that is quite common, which is they were doing one connection per thread, which isn't terrible. It doesn't scale well, but it doesn't matter that it doesn't scale well unless you want to scale hugely. And of course, Amazon does want to scale hugely. And in their case, that was, I would say it's a design pattern bug rather than an implementation bug. But they also have the top issue here, which is the monitoring was inadequate because they weren't actually checking for resource exhaustion in their system. So this is a file handler. So they should have been monitoring the file handlers on their system, and they should, and had they been doing that, they would have had an alarm on it and seen that the file handlers were reaching the limits. It didn't. Consequently, they actually the cost of failure was that they were expanding their system. They increased the number of connections beyond the number of the nodes, beyond what the nodes could handle, and it caused a cascade of failures. So something that's quite common with all of these really expensive ones is a latent bug, but also a cascade of different failures, not just one failure. And the reason this bug is particularly bad is because most site reliability engineers, SREs, are looking for the recent change. Something was rolled out, and that's true. That's a good pattern because most problems come from a change that's fairly recent. So when it's a change that is quite a while back, it becomes really difficult to find. So this categorization is a very good one for your incidents, to categorize your incidents against. Rollout procedure is kind of obvious. Insufficient testing is not really, I mean, obviously insufficient testing sounds like obvious, but what I'm talking about here is quite often you have, you're doing a nice feature coverage when you roll out your first version, but then as you add features to your system, you forget to add testing for the new features. And that's very common to miss that. The one after that, failures ignored. This is quite common with pipelines becoming longer and taking more time. They start to go out in parallel. So you have the performance testing pipeline there and the feature testing pipeline and deployment all in parallel. And then after a while, you begin to start ignoring the other pipelines. You just worry about the deployment one and you ignore those failures. And that becomes quite common. And there's something expired is, for me, it's probably the silliest and maybe the most common. And it's actually the most common for a global single point of failure. So certificate expiry is, it happens all the time, and yet we still have failures from it. And one particularly bad pattern of rolling out certificates is that you use the same certificate in all your regions. So like the reliability engineering 101, initial, early stage, basic reliability engineer, you use a different certificate for each region so that they expire differently at different times, because otherwise they expire and you just get all the services at the same time globally. Yes.
How does that work if you're using something like CloudFront?
Well, CloudFront doesn't necessarily have to provide a certificate. And there are increasingly numbers of vendors sorry, I'm not sure if you heard online, the question was what happens if you're using something like CloudFront, some CDN provider. There are increasingly vendors who you can integrate your certificate rollout with, and they will provide a certificate renewal mechanism, which is all automated. And a lot of enterprises are beginning to use those. But regardless, even if your CDN is providing it, you can still define where your certificates are and ask for a separate certificate for a different region.
Mm-hmm. Great, thank you.
So as I said, yes, the vast majority of incidents do indeed happen after a rollout, after a planned rollout. I don't know the percentage, but it's high. It's over 50% happen like that. When we look into this in the enterprise I've been involved in, it's like 75%. And so the single most important thing you can do, if you're starting from basics and you want to put reliability into your system, is this: add in a rollout capability and a rollback for that capability and test it. So our entire industry has moved gradually towards undo capability. We used to have word processors that would save your changes auto-save every 5 minutes. If you were lucky and it wasn't badly configured, or you'd lose everything. And if you lost something, you've not really lost, you're at least happy that you lost the last 5 minutes. But we all have horror stories of, oh no, that didn't work, or we're using something that didn't have that, or we didn't, and we lost a month's worth of work. That's terrible. Our industry has moved. Look, all the Google Docs, the Microsoft Docs, all of the online docs have moved to saving every change. Every single change is saved, which means that you work much faster because you're not worried about losing anything. But it's also, you can roll back and you can undo. Undo works really well. If you looked at any of your docs, and you can see the history, and you can go into the history, and you can actually look at different versions of the history and see the changes, and you can undo to even parts of it, and you can undo back to where you want. And our industry generally has moved to putting in undo capabilities, and that works also for deployment. And this is the most important thing. If you don't have it, put an undo capability into your deployment capability, which is a rollback that works, that's tested. So you have to make sure that it's tested, because a lot of times the rollback isn't tested. Yes, we have another question.
We've had a big debate on my project about this, and it was decided that in general, the cost of testing the undo that you're going to use like 0.01% of the time is greater than the benefit that you get from it, because it slows you down in terms of shipping functionality. And in many cases, the rollout is actually a series of steps, each of which depends on the previous one, and you have to undo them all if you're going to go back to the previous state. So we just generally diagnose a problem, create a branch off the release, and fix forward.
So, I mean, in a slide in a moment, I'll have a major deployment target should be one-click deployment. You should avoid multiple steps in the rollout as much as you can. But the reason that it's expensive for you is likely because you've got a lot of manual steps, but also it's a big thing. A rollout for you is a big thing, and it shouldn't be. What it should be is something that's you do often quite easily without worrying about it, because you'll have an integrated monitoring capability that will find. In fact, I'll just go on, because I'm just about to talk about this. I keep touching that. So, I'm just about to talk about this. So obviously minimal manual steps, as I said, and that's because as Facebook learned, human error is going to happen. So the more you can eliminate human error, the better. Checklists help if you're going to do any human activity. And artifacts well defined, actually, that's a standard kind of thing. SLOs, nice buzzword for our industry, service level objectives, are the targets for your requests, your latency, your throughput, and alerts against those. Clear smoke tests, but this next section here, which is how to do that deployment best practice. So a good practice would be, these aren't alternatives, by the way, you can do all of these at the same time. A good deployment practice would be to have the new version, so your old version, you've got the old version deployed, you put the new version out, you put it in a little cluster. It's going to take, say, 10% of the traffic. Also, you create an equivalent cluster of the old version, also with 10%. And that means that you have 80% going to the old version of existing, and then 10% going to each of the canary version and the baseline version. And that's what they're for. And if you have automated monitoring capabilities, this is a very simple, straightforward thing that you can do. And if you look at all of the main characteristics of the metrics that are provided there, you can very quickly and automatically see if there's a degradation in the canary and rollback. And if you bring in these best practices, then you'll see the benefit of testing that rollback procedure, because it happens a lot. Instead of it being something that we're going to carefully roll out, which is impacting your velocity enormously, it becomes something that's just automatic. And you just do the rollout and it rolls back if there's a problem. And then you've got and once you start testing the rollout capability, you'll test the rollback capability in the same way. And I suspect with a lot of manual steps, you're probably not testing the rollout capability that much.
Yeah, we're using Terraform infrastructure as code.
Yeah.
And
which does work.
It works, yeah, but some of these principles are much more difficult to apply because you haven't got the right tools.
Terraform is becoming fairly standard and it works quite nicely. I mean, I'm assuming we're pushing out to a cloud, or multiple clouds maybe. And Terraform does work nicely, and it is it's reusable. It works very nicely, and it's got that nice thing that our industry is moving to where it's the end state that's targeted rather than the process. And that's great, and that really works nicely. I would say that these are achievable on the basis that I've seen a lot of enterprises gradually move this way.
And then the specific problem we have is if you've done some refactoring in your infrastructure code, you need to run a series of scripts to migrate the Terraform state, to move various resources about, and actually writing the inverse of that is not trivial.
That's not, so what you don't want to do is write the inverse. What you want to do is take the previous rollout and then just achieve that same end state.
Well,
previous one.
Yeah, we could probably save a version of the Terraform state file and revert to it. Yeah.
I mean, if you look at the way data management versioning works,
Yeah.
you can do it a similar way. Okay, so these various, in case you don't know the rollout patterns, I mentioned canary, and blue-green is where you have entirely a full deployment of the old and the new system. That's another cost that Amazon has for their DNS system, because it's 100% guaranteed. That means that if there's a problem in either of the systems, they need to switch all the traffic over to the other one, which means that they have to have a fully capable system rolled out globally across hundreds of Amazon zones. Yeah, very expensive to do that. And AB is where you have your features, but they're not live when you roll out the new version, and you turn them on selectively. And this is becoming incredibly popular with machine learning, because machine learning has a lot of features, and it's a lot more than AB. It's AB up to Z. It's called multi-armed bandits or octopus. There's an octopus in there. They use a stochastic analysis version to gradually reduce the feature set down to the ones that are the most useful. So all of these, you can do all of these at the same time. They're not alternatives. So I'm going to switch over to something which is another system in that's taking over IT, Kubernetes, and you've got all these nice buzzwords. It's this, that, and the other. But in fact, Kubernetes is building reliability into your infrastructure. Now, don't worry if you can't read. It's not intended to read. So all the bits and pieces there. What I'd say is. By the way, if anyone's online, if you can tell me if there's any questions on the chat.
Yeah, not at the moment.
So Kubernetes is building reliability into your infrastructure. Now, anyone who's been in our industry for more than a few years will either have themselves or know somebody who has built a keep alive script or a daemon or a component, something that restarts the service once it dies. And Kubernetes does that for you, but it does a whole host of things. So I started going through the reliability aspects of Kubernetes, and I gave up after I had 15 different things, and there's dozens more. So this came out of Google, of their reliability system. Them building reliability into the infrastructure. It doesn't come for free because you have to, there's a little bit of overhead, and you have to get used to using it and understanding how to fix what goes wrong. But it's increasingly in our industry, we're moving towards building infrastructure, reliability into the infrastructure rather than have the applications do it. So if you can take out anything that the applications don't need to do, that gives them more reliability. That helps. And this is the reason why Kubernetes has just taken our industry by storm, because essentially a lot of things that the operations team, DevOps teams have to build themselves, they now get for free, and they learn one standard product. And another interesting thing about reliability is the domination or the increasing domination of NoSQL data stores. And this is so we have a CAP theorem, CAP theorem, which says those three letters. So there's consistency, availability, partition tolerance. This is a fundamental computer science theorem, and it says that at any one time, you can only have two of those. You can't have all three at the same time. So you're interested in the intersections there, the CA, the CP, the AP areas. You can only have two. So the question you have to decide is what do you want for your data store? So over on the CP side, that's the top right on that side. Well, that side. Those are caches, basically. So if you think about it, they give you consistency in that if you make a request, if they're there, then you get a result. If there's a problem, they go away. But it doesn't matter. That's the whole point of a cache. A cache is something that can disappear because you can restore all of the data from your primary data stores. That's great for caches, ideal. That would be terrible for a data store. All your data disappearing. And then over on the other side, you've got CA, and that's consistency with availability. That means it's not handling partition tolerance. So if you want a distributed data store, you're going to not have responses. So consistency and availability is something you desperately need consistency for a payment system. That's relational databases. You make a payment, money is transferred. You want it to be no error and no possibility that there's a lag between one thing and another. As I can't remember, is it the Ecuadorian country that's just found out, the one that went and made Bitcoin into a valid currency for the country, and they had their app, and the app, in order to enable vendors to have like if you go into a restaurant and you want to pay, you want to have some guarantee that what you're paying and what they're paying is the same thing. So the app froze the money, the amount, the exchange rate for a minute. And of course, Bitcoin is very volatile. It can move quite quickly. So a lot of people just played off that minute, and then they bought or sold within that time. And so they had to, and they're making a lot of money off the country because the country was paying for that. So they had to freeze that capability. In a payment system, you need that consistency across the system, but you don't have a petition tolerance, which means that you can't distribute it. So payment systems, that's why one of the reasons payment systems tend to be a long process. It's why you see a big delay when you're clicking that button to have the transaction occur. It has to go to a single location, guarantee that that happens, and come back to you. Most of the data that we have in all of our applications, social media, tweeting, Facebook's updates, it doesn't matter if it's a few seconds late. If somebody makes an update and you don't see it, you don't even actually notice it. You won't know. So it doesn't matter if it's seconds, even minutes late. So that consistency for most of the data in modern enterprises is not needed. What's needed is availability, because you want your customers to be able to get data, even if it's slightly out of date, and the petition tolerance, because you want them to be able to get it globally, wherever they are, and however you separate out your system. So that's the AP area, and that's the AP area which is where most of the NoSQL data stores are. Cassandra and DynamoDB being possibly two of the biggest, two of the most popular, but there are lots of others. And this is the reason why NoSQL has started to dominate the data store area. And it's actually about reliability more than anything else. That level of reliability of accessing and available and having the data available has become that important. If you're talking, so going back to the first slide, I talked about it's about failure management. So failure management means you have to decide just how much downtime it's acceptable for a particular service to have. But of course, each service is different, and some of them are more important than others. Some of them you'll find with them having downtime for a reasonable amount of time, and some of them you want them up within seconds or very little outage. And it's very difficult to do a scale of 1 to 100 and categorizing all your services at points as well. So it's quite common to just categorize them in tiers, 1, 2, 3, no tier. And that's about how available your service response is. Batch services, doesn't matter if it fails, you can do it again. The most important, whatever it is you do within your service, which might not be payment systems, it might actually be your landing page, because that's where you're getting in most of your customers. That might be the critical service, but it's up to you to define that. But it is important to make this tiering assignment so that you know how much effort to put into making them reliable. And then there's the different types of tests and the 7 tests that we've got. And it's nice if you can put more and more of them into your CI pipeline. If you can't, you can't, but put in as much as you can into your CI pipeline. And there's one here, chaos testing, which increasingly is the one that's happening in production. So chaos testing, if you've not heard of it, is where it's not, as the name sounds, chaos. You don't just randomly do bad stuff to your production system. What you do is you come up with a hypothesis. So, for example, I have a hypothesis that if a random node in our system goes down, our service will be uninterrupted because we're running on Kubernetes, and it will put the service, it has replicas, and it'll put the service on a different node. We start them on a different node and it happens. So then you should test that. And obviously first test it in test, but once you're comfortable that it works, test it in production. Kill a node every once in a while. There should be no interruption, and there's no real cost to it, because the deallocating a node and allocating a node is the same as having a node there. And there should be some startup. When you do these kinds of tests, what you find sometimes is that your system is perfect and doesn't have any problems. Other times you find that there's like a startup penalty for some of your services, and then you start looking at those, because although it sounds like, well, I'm only doing this in testing, it can happen in production by itself. So you want to have that capability. What tends to happen more is that as you come up with more and more hypotheses and you test them, you find that some of them have real problems. Deploying a Kubernetes cluster in multiple zones or data centers can be particularly problematic because unless you do the configuration right, it doesn't balance services very well across different data centers, different zones. And then what you can have is if an entire zone goes down or a data center goes down, which does happen, rarely it does, then you think, oh, it doesn't matter, I'm in these other ones, I'm fine. But actually your services are unbalanced and it takes down the service, and often you have other services dependent on that service and you get a cascaded failure. So you wouldn't expect one data center or one Amazon zone to lack of that to cause a systemic failure, but often it does. So these hypotheses are really worth testing. And that's an example that we actually found. So these hypotheses are ones that are good. You test them in test first, but then you carry on doing it in production, and it gives you a very good level of confidence in your system. So this picture over there on the right, whichever the right on the screen, that's the Falcon 9 rocket engine. Okay, so this is SpaceX. If you've seen them, I think it was about a month ago, maybe 2 months. The SpaceX Dragon flight with 4 astronauts who were not military trained, so there was no trained pilot amongst them, went up, and they all had a nice flight and they came down. So it's 4 civilians. They had some training for going into rockets, but there was no trained military pilot, and that made quite a lot of news. That's the latest in a long process for the SpaceX Dragon program. The first commercial flight was back in October 2012, and it was delivering supplies to the space station. And it was all the SpaceX ones, the Dragon rockets, use this engine at the bottom. It's a Falcon 9. It's got 9 engines, that's why it's Falcon 9. It only needs 7 for normal flight. So if 2 of the engines cut out, then it's fine. It can carry on and finish the project, the particular flight that it's doing. On that October 2012, first commercial flight, one of the engines did actually fail. So it didn't have a problem. The flight continued. And it's very interesting as an example of fault tolerance because there was a fault in one of the engines. None of the other engines had a problem with that. The rocket as a whole didn't have a problem with that. It was tolerance to that fault tolerance. And it has 2 extra engines. That's a redundant configuration. And with one engine going, with them losing capability of one engine, that means that the flight would tilt. It would start going in the wrong direction. But they recalculated the flight plan in real time, and it carried on as normal. And that's a high availability. So it managed to handle that very nicely. So that's a really reliable service, and I think it's a really nice example because although actually there's a lot of IT in there, it's kind of a very physical, reliable service. I like that one. So moving over to reliability for developers and architects, it's important to understand what you're talking about at that level. So there's 3 things there. So availability is kind of obvious, just how much time is your system up or not down. Resiliency is the ability to keep working in the face of a failure. It might be with a degraded response, it might be with a full response. And this last one, adequate performance, is integral to the whole aspect of reliability, because and this is something that you see every day, when you go to browser pages, you go to dozens and maybe hundreds of browser pages every day, and every once in a while you see a page that doesn't respond quick enough. And then you just give up on that site and you go to a different site, or you'll do a reload. That is showing lack of adequate performance. And you having to reload or giving up on it shows that it's not reliable. Reliability is about the usability of your system. And if people stop using your system, that's not reliable. So adequate performance is an integral part. It's not enough that it just be available and resilient. It also has to provide service in good time. And then there's some high-level resilience concepts. They're fairly basic. Data replication, you should get that with your data store, but you might have to build that into your system if you're doing something different. Process replication, that's something we see all the time with clusters, where you have multiple instances. Container isolation is about, if I have a failure, this is going back to those rockets, if I have a failure, I want that contained so it doesn't affect everything. It wouldn't be very good if one of those rockets fails and it blows up and then destroys everything else. That's not containment. Containment is, I have a failure, it doesn't affect the rest of my system. You isolate it and you contain any problems. Fast elevation, high availability, these are all fairly standard concepts. This is, although it's not hugely important failback, I like to mention it because there's only one letter difference between failback and fallback, but they're two completely different things. Failback is after you've failed over. So if you've had a problem and you fail over to another system to take over the services of that problem, and then you fix the original system, then you want to fail back to the main system. That's a failback. A fallback is when you make a request of some kind, and for some reason you can't provide, and the biggest example is streaming. So for some reason you can't provide the highest definition, you fall back to a lower resolution, lower definition streaming capability. So that's a fallback, is a less but still useful response. And fail fast is important because if you're going to have systems which can take over, you want them to take over as quickly as possible. Otherwise, you're eating into that inadequate response time. So you want systems that are going to fail as fast as they can. And then graceful liberation is fairly standard on exactly what it sounds like. And these, so this is, as I said earlier, the whole concept of Kubernetes was building reliability into infrastructure. And these resilience patterns, you get most of them with something that's called a circuit breaker. I'm a Java developer, so I know about resilience for J, which is circuit breaker, and you'll get all of these in there. You'll get timeouts, you try bulkheading. Although it's called a circuit breaker, there are different concepts in there, has them all. But what our industry is trying to move to is to abstract this out of the application so that the application doesn't need to build it in. So there's a new thing called a service mesh, which you may or may not have heard of. Istio is one example, and they're trying to integrate it into Kubernetes, but it's not mature enough. So one issue that operations people have is what happens when things go wrong? How do I know what the problem is? How do I fix it? What else can I do? And with Kubernetes now, you've got a lot of examples. It's much clearer, and if you see something happening, you can look it up, and it's fairly clear. With the service mesh, we're not anywhere near that yet. So service mesh is not anywhere as common, because if it works, it's beautiful. If it doesn't work, then it's really hard to figure out what the problem is at the moment. That'll get better. So the service mesh takes this out of the application and puts it into the infrastructure, which is great because then you can reroute requests at the operations level. You don't have to worry about it at the application level. This is another article I wrote about, which is about availability and performance. In this case, avoiding overloading. And I was really surprised when I wrote this because we were actually looking at how to avoid overloading, and we found that there were very, very few things that you needed to do. In fact, there's very few options available to you. There's only 6 options available to you. So the top 3 there in the little diagram is about giving your system enough capacity to handle all the requests. So you scale your system, or you over-provide, which is you provide, you pay for extra capacity, or you queue if your architecture allows you. You queue requests. But ultimately, nobody has the amount of money that allows them to scale infinitely. So even Amazon. So at some point, that's limited. And then when it's limited, when you hit the limits of that, handling the capacity, then you have to deal with what to do when you don't have enough capacity. And those are the three at the bottom. The first one is just dropping requests. And that's those, when you do a browser request and you get no response at all, it just hangs there. And eventually your browser comes back and says, sorry, I didn't get a response. Maybe there's a problem with the server. That's where they drop the request. It might not have been an intentional dropping, but it could have been. It could have been just them being overloaded and dropping requests. Rate limiting is the next step where instead of dropping requests, they process the request, but doing a very fast pass, they return an error. So they'll return on 404 on your page. Actually, in HTTP, there's an error code 429, which is specific for rate limiting. So that's better because at least you're getting to the server, you know that you're getting some sort of response, and I'll probably say try again later, we're really busy. You must have seen that kind of page. And the last option here isn't something that you can do on the server. It's the server and the client together, because what it is it's just the rate limiting on the server, sending the error. But the client then picks up that error and says, oh, actually, I'm sending stuff too fast, I will send it slower. So that's back pressure. That back pressure is a cooperative dance between the client and the server, where the server says, whoa, slow down. And as some of the organizations like to put slow down tiger for some reason, that's quite common as an error message. And then the client just reduces the rate of requests it's sending. And those, if you're handling overload, sorry, I'll just say that, you're handling loading, overloading, that's it. Those are all your options. There aren't any more. It's nice and simple to think about. Not necessarily simple to implement, but simple to think about. And then the second thing about a page about availability and performance patterns is you should have all these standard things. Again, SLOs, service level objectives, they're the targets for your throughput, latency, your errors, saturation, whatever it is. Normally, you want to focus on your business. So it's business requests and their latency and throughput. And you don't want to have too many SLOs. These are the things that are important for your business. And your dashboards with alerts and all of these things should be standard in your system along with health checking. See how we're doing. Okay, and so down there, APM, that's application performance monitoring. And that's the tool that's for observability. Observability is what lets you see what your system is doing and looks at all the metrics. So the buzz, they're called their three pillars: logs, matrix, and traces. But APM is a tool. I work for a company called Elastic, which is, can't see the logo, it's off the screen. It's below the bottom of the screen at the moment, but I work for Elastic. They do Elasticsearch. They also do Elastic APM, which is a very good APM tool. And you can use it for free, potentially. Depends on exactly how you use it. If you want to use some of the more advanced features, then as most enterprises would. So I think I'm almost just a couple more slides. So going back to what I said earlier, usability. Usability is massively important in reliability. The less usable something is, the more likely people are to make errors. And the more they make errors, the more errors there are in the system. And well, as Facebook found out, you want to cut down on errors if you can. So you want to make things as usable as possible. And you don't want to have your release pipeline with lots of manual steps, because that's less usable than one click. And then it's usually not the network. But the trouble is, when you start troubleshooting, it very often looks like the network, because that seems to be, things are going slow. Well, that's because you used to have, there are network problems. So it's often an immediate culprit, but it's often, very often, not the network. But when it is, these are the things that it tends to be. And finally, really important, not just documentation about the service, but think about the situation where something's gone wrong and somebody who knows very little about your service is coming to have a look at it, and it's not you because you're asleep and you don't really want to be woken up in the middle of the night. So it's somebody else. You want some simple overview, a very quick overview that's easily understandable, what roughly the service does, so they can put that into their mental context. And then ideally some simple steps for them to follow to figure out what the problem is, especially anything that's standard. And then the process documents about what to do and who to contact when they can't figure out what the problem is. So all of these things are really important to keep up to date as well. Have them and have them up to date. Yes.
I've recently been doing some of this, and I find that debugging a program that basically runs on human software, human hardware, is the most difficult thing in the world.
Yes, obviously, well, not obviously, but yes, people. Okay, and that was it. That's my slides. This is me. I have fun with Java agents, and I have one more slide, which is actually the earlier slide, which is just that if you're coming to this fresh, or you need the biggest bang for your buck, expression is, this is where I would start, where this is the thing that would give you the biggest reliability improvement in your system if you're not there at the moment. And that's it for me.
That's super. Thank you for the advice there. Thank you. I don't know if you have any questions.
I've got one. I was wondering about monitoring. So my experience of monitoring is a dashboard and alert event. The other is alert. And so I was wondering, like, what would a good monitoring system look like?
The question is, what would a good monitoring system look like? The example was a dashboard with an alert. And a dashboard with an alert is something that makes people comfortable.
Yes.
A good monitoring system is automated as much as possible. So with that rollout example I gave you, where if you set it up correctly, the new version, the old version are in very separate little clusters, and you can do a direct comparison. You've got the same number of instances with the same amount of traffic going to each. You can do a direct comparison. So what you want to do is try and have baselines that you can compare anything against. That can take a little while, because if you have an existing system, you need to generate that baseline, which might be the last 2 months, 3 months worth of traffic, and all the metrics that are associated with that. And you need to make sure that you've taken out any incident areas. But if you generate those baselines, then you can very quickly see where there's anomalous behavior outside of those baselines. And all of the monitoring systems are moving towards machine learning that does exactly that. It identifies a baseline of the current system, smooths out any anomalous, assumes that there's going to be some sort of smooth pattern, and then looks for comparisons against that, daily, weekly, monthly, some understanding of patterns across the year, so highs or lows, depending on your industry for the winter season, things like that. And then you can come much closer to some kind of automated capability that allows you to identify when there's an anomaly. So that's really, all the monitoring is there. There's two reasons. One is you want to generate an alert when there's an anomaly, and the other is to troubleshoot. So I'll go to the first one. Alerts have to be not very many.
Agreed.
Yes. So it's really important that if you're getting alerts all the time, then you implement it incorrectly. You have to get rid of lots of alerts. So there shouldn't be very many alerts, and all alerts have to be actionable. Because if you can't do anything about it, there's no point alerting about it at all. That's a report that you want to send to somebody to say, oh, I don't know, we need to put more money into something. Alert has to be actionable, and it has to be ideally anomaly that's detected automatically. There's no point in asking people to look for anomalies because they will see them, but they're not around all the time. They lose concentration. And even where you have a 24/7, they're not going to stare at a monitoring screen the whole time. Then it's just pointless, a waste of time of people. So you want to automate as much as you can. The way you automate is by having baselines that you can compare against, and alerting that's very targeted at not having too much noise. And there's I can't remember the exact thing, but you should have your alert should have an owner, because alerts change over time as to whether they're still usable, as something that's still viable. So if there's an owner, then every time there's an alert, the owner has to look at the alert and say, okay, do we want to change the parameters of the alert? Do we want to get rid of it completely because it's no longer valid? So you should have an owner, it should be actionable. And if you've got too many alerts, then I don't know, wind them all right back, start again from scratch. But yeah, that's it. Baselines to have automated monitoring and alerts that are handleable.
So how do the alerts reach the actual owner?
You can answer that.
Well, I was about to mention the same question. The system I'm working on at the moment, we've got a system called Observability, which basically you can send the alerts into, and they've got a schedule of duty engineers who receive those alerts. And you've got an app on your phone that you can acknowledge them and that kind of thing.
So the question was, how do you alert? All systems that are, and any large enterprise will have loads of different ways of getting them. Integrations with Slack, integration with PagerDuty, integration with Twilio or Vonage to send you a text. Or all of these integrations, if you don't have them, they're actually very simple and straightforward to do. And that's how you alert people. Emails if you can, but you want to alert people on the few things that are important, and you want to get to them on a communication mechanism that they don't get a lot of other noise from, so that they pay attention to it. So emails tend to be, I mean, there's the Night Capital example where they ignored the 77 emails that told them exactly what was going wrong because they had 10,000 other alerts.
It's exactly the situation.
Which is, yeah, you have to wind that back so that if you're using an email, then there should only be the 5 alerts, but however many they're actually going to look at. Once the alerts happens more than a certain number of times and they ignore it, then they'll ignore it forever. Which is why you have to have an owner for that alert. So every time it happens, you have to say, what happened to this? What did we do? And do we need to change the parameters? And simply giving every alert an owner that they then have to look at every single time that alert is called can often just reduce the noise enormously because they don't want to spend all their time looking at it.
Yeah, it's going to spam that. Yeah. No, that makes sense. Thank you.
Yeah, I've also used something used X Matters. X Matters is another one of these distribution systems, and it could send SMSs and has its own app and all sorts of channels. Where Observability seems to score a good point is because it recognizes repeat alarms of the same thing and basically doesn't create a new alert for you.
Yeah, that's good. That's best practice. Check. Can anyone tell me if there's any online?
Yeah, I've been looking. Not so far. People have applauded and basically said, thanks very much, got to go now. So I think we can bring it to a halt and network a little bit more. There should be some more food and drink next door. Thank you very much indeed, everyone.
Thank you.
No expense.
I'm just learning. Okay, so it's very good. Functional.
We've got specialist groups. About 20 people on the BCS website, 20 or 30 specialist groups. We have local branches. We have here. Once we get going. So before COVID, we were several meetings a week with different groups on different topics.
So dynamic testing is really about
It's not including software development.
Sorts of
it's
So
Or is it just?
those are okay. They're a different. This is a different area completely. So it's
Yes, you-
dynamic is just about adapting. They have these tests where